Sweet.
Hi, how are you doing today?
Oh, pretty good, it's raining out.
I see you have a poncho and an umbrella.
That I do. That's actually for redundancy. If you didn't notice, I'm also wearing contacts underneath my glasses for the same reason.
Okay, what can I get you today?
I'll just take a coffee, please.
I'll be right back.
Thank you. What the heck is that? What is that?
Here you go, enjoy. Let me know if you need anything.
Thank you.
The word resilience originates from the Latin verb resiliere, which means to jump back or to recoil. The concept of resilience has different meanings depending on the field of study, but are all analogous to the Latin definition. For example, in material science, the resilience of a material is defined by its ability to absorb energy when it is deformed elastically and release that energy upon unloading without being permanently deformed. This is like when you stretch a rubber band and expect it to return to normal. But don't stretch the rubber band too much or else it will break. A permanent distortion that has shown us the resilience limit of the rubber band. During natural disasters, for example, lightning strikes and flooding can down power lines and knock out power stations, which puts stress on the system, like when I pull on this rubber band here. Enough of these events occurring in the right places can push the system beyond its limits and cause widespread and long-term power disruptions. Luckily, you might only experience a power outage once a year because of the high resilience of our power grid here in the United States. The Presidential Policy Directive, PPD 21, defines the resilience for critical infrastructure sectors as the ability to prepare for and adapt to changing conditions and withstand and recover rapidly from disruptions. Resilience is based on 4 attributes of the system dealing with disruptive events. 1, the capability to withstand. 2, the speed of recovery. 3, the ability to adapt, and 4, the ability to prepare for the next event. These will be discussed later on in this video.
First, let's talk about what can cause a disruptive event. When talking about resilience, we are interested in the power system's response to abnormal or disruptive events. Disruptive events can be deliberate attacks, accidents, or naturally occurring incidents, and are characterized by their effects on infrastructure, duration, and intensity. Disruptive events can be human, physical, and cyber domains. These types of events can be classified as direct or indirect, natural or man-made, or forecasted or anticipated. Hurricanes and storms are examples of disruptive events that can be forecasted. These events typically include intense winds, coastal storm surge, lightning, or flooding. Direct effects may include damage to electrical components, or indirect effects can include fallen trees or obstructed roads. This can prevent workers from getting to repair sites or even operators from getting to a power plant or distribution station. Tornadoes are an example of a disruptive event that can be anticipated in occurrence, but the exact path cannot be forecasted. Economic disruptions are an example of a disruptive event that cannot be anticipated. This can include decrease in availability of capital, decreased revenue, increased costs, all of which affect infrastructure like reduced maintenance, less skilled workforce, or aging infrastructure not being updated. Other events may include ice storms, earthquakes, volcano eruptions, wildfires, droughts, geomagnetic storms, pandemics like COVID-19, cyber or physical attacks, or other social disruptions, like retirement of skilled workforce or policies and regulations, or accidents, which are actually the most common type of disruptive event. An example of this is the 1986 Chernobyl nuclear power plant disaster in Ukraine, which caused fatalities from radiation due to a flawed reactor design combined with human error. Resilience of a single load is defined by the uptime, or the time the load was in service, divided by the duration of the disruptive event. This means that for a given event of 24 hours, if the load was in service for all 24 hours, that would be a perfectly resilient load with a resilience of 1. If it lost power for 12 of those hours, the resilience would be half. Here, we can mathematically see the effects of the 4 resilience attributes and how they lead to improving the uptime. The ability to withstand an event means the system can stay online and be completely resilient for that event. The speed of recovery will maximize the uptime in the event of a power disruption, and the abilities to adapt and prepare to improve both the capability to withstand and the speed of recovery. This number can be improved by using backup energy storage or generators, but further mathematical descriptions of resilience will not be useful for the purpose of this video. This ratio seems like a simple metric, but actually includes a series of aggregated data over time to predict the expected resilience of a system for future events. Since we have 3 power grids here in the US, which are also subdivided into smaller sections, one resilience metric for the whole country doesn't really exist. For resilience, just keep in mind the ratio of uptime to event duration. There are multiple phases of the disruptive event cycle, and each attribute of resilience overlaps with one or more of these timescales. The event duration is followed by the immediate aftermath, and then the intermediate and long-term aftermath up until the next event occurs. Let's start with the capability to withstand. This takes place during the extreme event. The strength of our system and how much abuse it can take during a disruptive event is the capacity for withstanding the actions taken by the event. Activities during this phase are focused on survival and targeted response. During the immediate aftermath of an event, we see the speed at which the system is able to recover. Elements that were affected during the extreme event are repaired or reconstructed, and service restoration takes place. Activities during this phase also include evaluation of a system status through field assessments. Recovery speed is a key aspect that was not exemplified by the rubber band analogy from earlier. When Santino stretched the rubber band, it immediately returned to normal after he let go. However, with a power system, lines don't just magically fly upright after the rain stops. For this reason, the recovery speed can take months, like in the case of Hurricane Katrina. The intermediate aftermath starts once repairs, either temporary or permanent, are mostly completed, and this is where adaptation begins. In this phase, lessons from the extreme event are learned by performing forensic analysis, for example. Power companies and universities will send out groups of researchers to disaster areas to study the effects and quantify weak points to help adapt and make a more resilient system. This also plays into preparation schemes for disruptive events. Dr. Alexis Kwasinski from the University of Pittsburgh is an expert in this field and has contributed significantly to advancing power systems resilience. We've been fortunate enough to learn this information firsthand in his Power Systems Resilience class offered at the university. Power systems might adapt to lingering effects of the last event, such as economic effects of a reduced load in power grids. For example, if an entire neighborhood is destroyed and won't be rebuilt, then why rebuild the power systems for that neighborhood? This learning process is an essential component of the adaptation mechanism that is then applied in the next phase when the necessary changes needed to improve resilience for the next event are planned. Adaptation occurs during the beginning of the long-term aftermath and up through the beginning and planning of the preparation phase. Planning and preparation activities focus on preparing for the next event through planning and mitigation of known vulnerabilities. During this phase, infrastructures may be modified in order to make them more resilient for the next event. Such infrastructure modifications are made without certainty as to where and when the next disruptive event will happen. This uncertainty involves a cost associated to the preparation decisions, which are usually assessed and evaluated using risk analysis techniques. At Eaton, we work with many customers to develop contingency plans to prepare for disruptive events, and we often uncover unforeseen vulnerabilities. Planning and preparation occur until the next disruptive event, where the cycle begins again. Over the years, this iterative process has taken place to yield the resilient power systems that we know today.
Now let's take a moment to expand on the effects of disruptive events. There is more to be concerned with than just knockdown power lines or flooded substations. Based on the National Institute of Standards and Technology's reports, we can classify the overall power system as a community interaction between three distinct critical infrastructures: the physical domain, the cyber domain, and the human domain. The physical domain is obvious. It consists of the physical grid infrastructure like power lines and substations mentioned before. The cyber domain is the communication network that controls the power grid and its information like voltage sensing data. This domain overlaps with the physical domain because there are physical communication buildings and towers that also need power. The human domain consists of the processes, policies, procedures, and regulations, as well as the system operators and administrators necessary to manage and operate the power system. This is where a lot of mistakes can arise and cause disruptive events. People are just as important as the technologies they are using for the makeup of a resilient power system, so human error is a significant consideration for resilience. All three domains comprise the overall community system in which they interact and affect one another. For example, information from the cyber domain affects decisions made by the operators in the human domain. This community interaction leads to interdependencies between the critical infrastructures. For a large system, these interdependencies start to get very complex and computationally expensive. There are many terms that we associate with resilience, but it is important to keep in mind they are not interchangeable. The concepts of resilience and reliability seem analogous, but are fundamentally different in this context. Resilience is a system-level characteristic that is measured as a response to an abnormal event that can cause a disruption in the power. Reliability deals with individual equipment and is a very precisely quantified trait. Reliability is measured by the mean time between failures, mean time to failure, and mean time to repair under specified conditions. This is critical information to know about the components of your system so that you can reasonably expect it to operate for a given period of time. For example, here at Eaton, a typical design life is 20 years or more for electrical equipment and thus will not unexpectedly fail at a crucial time. Now, of course, reliable equipment can help create what we refer to as a resilient system. Unexpected equipment failures could in fact even cause the disruptive event, or unreliable equipment could further exacerbate the negative effects of a disruptive event and thus lower overall system resilience. For example, you wouldn't want a power meter failing in your switchboard and thus preventing critical data from getting to the main control system. Resilience and availability are analogous and quantified in a similar way, but they represent two different concepts. Resilience is the portion of time the system is operating during abnormal events, while availability is measured during normal grid operation and takes into account N+1 or other redundancies. For example, N+1 redundancy would be like how I'm using this lapel mic to record myself, but I have my backup boom mic hanging right here just in case there are audio problems with the lapel mic recording. You can consider a power grid operating under normal conditions to have high availability if it experiences very few outages. However, this highly available grid is not necessarily resilient if it is unable to withstand or recover quickly when a disruption or abnormal event occurs. The resilience is measured as a response to an abnormal event, while availability is measured over a longer period and takes into account planned outages for repairs or upgrades. So why is resilience more important today? Well, the short answer is because of electronics and their sensitivity. Let's compare our power loads today to 100 years ago. 100 years ago, there were pretty much two things on the power grid: motors and light bulbs. If you have a power disruption,
Alexa, turn out the lights.
Okay,
Alexa, turn on the lights.
okay.
The lights eventually come back on, and you can get back to making midnight marmalade or whatever you were up to in the 1920s. Today, we have sensitive electronic equipment like desktop computers and data centers that hold critical information. Imagine if you lost power and you couldn't load up reruns of the Puppy Bowl. But seriously, there are very critical communication networks that make our world go round, such as the stock markets, news, our cell phones, and pretty much anything you can think of like food delivery services, navigation, and the list goes on. An easier example is that of an alarm clock. If you set your alarm and the power goes out at night, what happens? It's blinking at 12 a.m., right? You're going to be late for work and hopefully not fired. If a data center drops out, it doesn't just kick right back on where it was, just like if your desktop lost power. Healthcare facilities, especially hospitals, are also critical and must be supported during disruptive events. For example, the National Fire Protection Association requires that life safety or critical loads in hospitals be up and running within 10 seconds of an outage, and backup fuel supplies must be sufficient to last 96 hours. At Eaton, we typically work with our customers to go beyond minimum requirements for such systems to help account for unexpected events. While safety codes typically address minimum emergency power requirements, other factors that we have mentioned may not be accounted for, and additional power system backup may be required for systems such as imaging and diagnostic equipment within a hospital. Power disruptions can be catastrophic in this day and age, and this is why power systems resilience is so important. Eaton is intimately involved in making our power systems more resilient. From the component reliability all the way up to utility system behavior, we think of everything as a grid of interconnected systems. Every component we make for electrical systems, including things like circuit breakers, fuses, relays, and more, are reliable and depended on for intricate coordination schemes to localize and remove electrical issues while keeping unaffected areas online. This prevents snowballing effects that can occur from minor faults of a single component, for example. For commercial and industrial power system designs, solutions like our advanced control and automation for microgrids allow companies to regain control of their power system during utility power outages. Options like load shedding schemes help you get the most out of energy storage and renewable sources. For utility systems, Eaton plays an important role to provide system stability using our power factor correction capacitors and voltage regulators paired with their respective controllers that can also be interfaced with our Yukon automation system for automatic response to abnormal scenarios. But beyond our products, we have a service group that is second to none in the industry. The products alone cannot provide resilience. Components can't do it alone. Now, to talk more about Eaton's Electrical Services and Systems Group is their Vice President and General Manager, Craig Gobb.
As an extension to Eaton's components and assemblies that comprise our customers' electrical systems, Eaton's Electrical Engineering Services and Systems provides a comprehensive portfolio of services. We possess specialized knowledge and provide power management solutions tailored for every stage of a power system's life cycle. Our services team spans across the national footprint with local operations across the country. Our services organization is uniquely positioned to contribute to all three aspects of resiliency. Number one, our capability to withstand. Eaton offers everything from simple transfer schemes to microgrids for our customers. As a group of individual components alone, a microgrid cannot function. Our service team provides engineering services and integration capabilities to tie together and control each of these components to create a robust distributed energy resource system capable of load shedding and bidirectional power flow. Number two, the speed to recover. Eaton has a comprehensive set of crisis response capabilities. These capabilities are highlighted in our ability to bring customers back up and running after natural disasters like Hurricane Katrina and Ike. Number three, ability to adapt. Leveraging our Center of Excellence, Eaton Services provides customers with insights and expertise they need when troubleshooting, designing, and upgrading their power management systems. Whatever your needs might be, Eaton's Engineering Services is here to help you become more resilient.
Okay, what can I get you today?
I'll just take a coffee, please.
I'll be right back.
Thank you.
This is an example of a resilient power system that withstood a faulted feeder. It had the ability to go back to its original state with minimal downtime. Our recloser and communication system, as well as utility operators, were all involved, connecting the three domains: physical, cyber, and human. In this scenario, with Eaton reclosers and the Yukon feeder automation system, the power was safely restored while the operator was on standby if necessary. To learn more about resilience and other power systems topics, contact us or your local Eaton representative to schedule a visit to the Power Systems Experience Center today.